got such a nice rate to it, the last day of class. But there's still a final exam, yeah. You guys have it on Monday, bright and early, 8 o'clock in the morning. Bring some coffee or pop. Actually, I used to not be a coffee drinker, but now I am. I used to drink pop sometimes in the morning. Sometimes I'd get to it with my job. When I went to summer, I had to start. One summer, I had to start like every morning at 7 o'clock, and I had like a whole thing of Mountain Dew. Not a good idea. Coffee's not a ton better, but at least it doesn't have as much sugar. Anyway, you can bring something else to eat as long as it's not smelly or noisy. You know, a donut. Well, maybe a donut's not a good idea. Something somewhat healthy might be better for you, and get a good night's sleep too. Today we're going to review for the final exam mostly, but I do want to finish with the pendulum as a Hamiltonian system and talk about that a little bit more. Do want to mention a couple things. A reminder, first of all, the course evaluations are due by Sunday, which is earlier than they have been in the past, so make sure you get that done. It is required. It's easy points. It'll only take you maybe 5 or 10 minutes, but it's not extra credits, so it hurts you if you forget. So make sure you do that. They are kept confidential, but I can see who's done them and who hasn't done them. Second announcement is that I did get the financial math actuarial course approved for next summer, but now I need to make sure I can fit into my schedule. So it's not a guarantee that it's going to be offered next summer, but probably it will be. I think it will be. I just got to think about it carefully to make sure it can work. But I'm 80 to 90% sure it probably will work. So I'll send you a note about that when I've got it finalized. It's not in the summer school catalog or course list yet, and it may not be since that's already been published. But there's about an 80 or 90% chance that I'll run it. And I'll run it even if there's only a few students in it. So. Probably also, just as another comment, probably as far as meeting for the course, we would meet whenever is convenient. It wouldn't be something where we would have to meet every day or every other day or what. You know, whenever we want to meet in the most convenient way, that's probably the way we would do it. The goal would be to help you study for financial math actuarial exam. That would be the main goal of the course. You would get credit for it, you do have to pay for it, but it would help you study for that kind of thing if that's something that you're interested in. All right, let's talk a little bit more about Hamiltonian systems and a little preview of some things in both differential equations and multivariable calculus, and then we'll do our more general review. So the pendulum differential equations. Well, first of all, there was a second order equation for the angle. The second derivative of theta with respect to time, where theta is the angle that the pendulum makes with the downward vertical, was a constant time, a negative constant times the sine of theta. And the sine of theta being in there is what made the equation difficult to solve, really pretty much impossible by hand. But we can approximate solutions on Mathematica. Taking the length of the arm, the rod, for the pendulum to be 1, we can just write this as negative g sine theta. That's one second order equation. Second order means it has a second derivative in it. You can convert that to a first order system. First order meaning it only has first derivatives in it. Let v be the derivative of theta. So v is really an angular velocity, not an actual velocity, but an angular velocity in radians per second, for example. And then the rate of change of that angular velocity with respect to time would be given by this equation, negative g sine theta. So that was our first order system. The benefit of first order systems as opposed to second order simple equations is you can make the phase plane, and also when you have the phase plane you can talk about numerical methods more easily. You can talk about how to approximate solutions more easily in a phase plane. You can use something called Euler's method, which is in section, well, there's a scalar version in section 11.2 of the book, But in differential equations, if you take that class, we talk about a two-dimensional version. So in Mathematica, I've got these functions, f of theta comma v equals v, and g of theta comma v equals negative 9.8 sine theta, representing the right-hand side functions. That's f, that's g. I went ahead and plugged in g as 9.8. You can't solve the corresponding system symbolically, so we need to use NDSolveValue instead of just DSolveValue. This syntax will store an approximate solution with this initial condition into this two-dimensional list. And then you can use plot to plot the functions in that list. There they are. So blue is the theta. It's starting up near the peak, and it doesn't move very fast at first because it's so close to the peak. You know, pi is 3.14 is almost equal to pi, not equal to pi, but almost. So it's going to move very slowly at first, and then all of a sudden it starts going fast to this opposite side over here. There's no friction involved, so this ends up being a periodic motion. It is somewhat analogous to a cosine wave, but it's not a cosine wave for sure. It doesn't have the same kind of characteristics. You get these flat parts here and here. The velocity is even less like a negative sine wave. It's so close to zero for a while that that's what distinguishes it from a sine wave. But then when you have the steep parts of the blue graph, then you get large negative or positive values for the angular velocity graph. I can put this parametric curve that consists of theta of t and v of t in a phase plane. And I can also, in the background graph, what we talked about as what's called the Hamiltonian function. V squared over 2 minus 9.8 cosine theta. It's essentially potential energy. The V squared over 2 is kinetic energy, if the mass is 1 kilogram. The negative 9.8 cosine theta, you might be wondering, how can energy be negative? Well, potential energy is kind of funny in that you can really take any given function that can work for potential energy and shift its graph to up or down. Negative 9.8 cosine theta can be thought of as a potential energy portion, and so the sum of those things is the total energy. And the fact that the solution curve stays on top of one of the level curves of that energy function, total energy function, is what makes, that's what's making clear that the total energy is conserved. This solution curve starts over here actually, it moves slowly at first, then faster and faster, then it comes over here and moves slowly again. In fact, I did make an animation, maybe in the second class I did this, showing the solution curve moving over time. It's a little herky-jerky because contour plot making the level curve of the Hamiltonian function is very computationally intensive. So it's not a real smooth animation, but you can see it does move slow at first, then all of a sudden coming so fast that it basically drew the whole thing there. It's not as smooth as would be ideal, but it does stay on the level curve. By the way, you can make an animation of the actual motion itself as well. Let me do that now. I want to make a manipulate. I'm going to make an animation of the actual motion of the bob moving back and forth. That's my goal here. How can I do that? I could use graphics. Well, okay, I'm going to combine graphics, so I need show. Graphics can be used to make, as we've seen, arrows. It can also be used to make other things like lines. Not just arrows, but lines. It can also make circles and rectangles and triangles, things like that. What line am I going to make here? As my animation parameter varies, I'll call the animation parameter B, as usual. Actually, here I don't need to start it just barely bigger than 0. I can start it at 0 because I'm not going to be plotting the graph of a function over some interval starting at 0. I'm going to be plotting the bob moving back and forth. I can start time at 0 here. What do I want here? I want this line to go from the origin down to the location of the bob as it swings. What would the starting location be? If the bob is starting, well, okay. This angle is theta. This point is going to be 0.00. This point here is going to be a point on a circle of radius 1. What will its coordinates be? If we were measuring the angle from the positive x-axis up this way, the coordinates would be cosine theta comma sine theta. We're measuring it from the downward position, however. I gotta think about this. I think we want the first coordinate to be sine of theta, and the second coordinate here to be negative cosine theta. Then, for example, when theta is 0, this is going to be at the point 0, negative 1, which is where I want it to be when theta is 0. And if theta were pi over 2, for example, it would be over here. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. I am at the right point when theta is pi over 2. This is going to give me the right coordinates of the point for where the bob is, no matter what theta is. Theta is a function of time, ultimately. So if I do sine theta, which is theta sol of b, because I want to plug the solution in this as v changes. Theta sol represents the solution curve in terms of its theta coordinate. Theta sol is just what I called it. That's the first coordinate, and if the second coordinate is negative cosine of theta sol of b, I think this is going to work. Although I might want to fix my plot range. That's actually the straight up position, or almost straight up position. And there it's swinging back and forth. Could I put a bob on it as well? Yeah, I could do that with list plot, for example. Actually, you can do it with graphics still, but I think I'll do a list plot. List plot. If I plot, once again, this point, and I think I need an extra set of curly braces to make this work. There's the bob. So it's starting almost at the vertical. So the motion's real slow at first, but then as it goes down, it starts speeding up a lot. There's your motion for the particular initial conditions that are made. Okay? That's pretty accurate, you might say, except we're assuming no friction. How could you add friction into this? If you go back to the original equations, a friction term could be something of the form over here. This is like that's the angular acceleration. A minus some constant, I'll call the constant k. That's not a spring constant. It's just another kind of, it's a frictional constant. Times, say, d theta dt here, which is the same as v. if I have like a minus kV here, see that? It's a K. Minus kV there, that should bring friction into play where K is positive. So let me go back up to my right-hand side functions and change them a bit. Actually, let me copy and paste all these. I want to keep the case of no friction here still. I'll put the case with some friction down further. If I add in friction here, it's the g function that has to have an extra term. Let's say k is 1. So let's just put a minus v right there. Now we should get some friction involved. Maybe it's too much friction. Well, that's not too bad. There's a good number of oscillations there. Still over 20 seconds. These graphs here. There's oscillation, but the oscillation is decaying to 0. Once again, the blue graph is the theta, the angular position, and the yellowish graph is the angular velocity. This time, now with the Hamiltonian function in the background, it does not stay in the level curve. Because mechanical energy, kinetic plus potential, is dissipating, it's turning into heat. Total energy is still conserved, but the mechanical energy is now dissipating. And so you see us spiraling in toward darker regions for the function, the Hamiltonian function. The energy means lower values. So we're spiraling in toward negative energy values. That's negative only because of the way we pick the potential energy here. Lower energy values is what we're spiraling in toward. Mechanical energy is not conserved. And this time the motion does decrease in amplitude in this picture too. So that it comes to rest effectively. Okay, so that would be more realistic. Maybe I should do one more quick thing before we go into our general review. Let's go ahead and keep the friction in here, but let's do something interesting. Let's pump up the initial velocity. Let's make that higher. Let's see what happens. So let's make the initial velocity not 0, but how about 20? That's really fast. I'll go up to 40 here. Huh, interesting. Now theta is not heading towards 0. It is still heading toward a multiple of pi, though. Multiple 2 pi. It's still going to come to rest because of friction. You're not going to see it in this graph. Here, it's going to go off the screen. In fact, we're not even seeing it at all because the initial velocity is too high. Let's make it smaller, actually. Let's make the initial velocity smaller. How about 10? You see the red graph, it's up there, just barely. It is still going off the screen, but that doesn't mean the motion is going off the screen. You still see the entire motion. It goes around the horn a couple times before it starts coming to rest. We gave it enough of a kick at first that it goes around at least once. Maybe a couple times before coming to rest. Okay, so this model can handle that kind of situation too. So that's pretty cool, I think. Let's do our more general review first. Now. And then we'll come back the last 15 minutes or so of lecture B and talk more about differential equations again. So our more general review, I think what would be most helpful might be to look at the old exams and maybe remind you how to do some of the harder problems. Okay? Not that the exam is all going to be the harder problems, but if you can do the harder ones, then hopefully you can handle the easier ones. So again, I'm going to take a sampling of old exam problems and then also add in some differential equations problems. I'm thinking, since I've got 2 sections of this class, now I trust that most of you are honest, but since I have 2 sections of this class, I think I probably need to make 2 slightly different versions of the exam, since you guys are taking the exams on separate days. Try my best to make them of equivalent difficulty, but probably some of the problems will be the same, but some may be different. So I think I need to do that, give 2 versions. And in fact, even within each individual class, different people will probably be taking different versions. Do you have a question?
Yeah, will you be using like every question on the test, or only like a sample? From
A sample, yeah. Yeah, if I combined the tests completely, it would be too long. So it's got to be a sample. So here's the mini exam. So let's glance over the types of problems that were on that. Talk about each of them briefly, perhaps, and then say, well, which of those was the hardest ones, and maybe give more details about how to go into solving those harder ones. So in this first problem, you want to find this integral, and you know the values of a couple other integrals. So that's a problem where you're using properties of integrals. You don't know what f of x is, but you do know properties of integrals. For example, the fact that the integral from b to a of a function is the opposite of the integral from a to b of the same function. Looks to me like that's one property you're going to need, because look, this is an integral from 5 to 4. Linearity property looks like it's probably necessary. So for example, this 3 should be factored out to solve for the integral of f from 2 to 4. So you can use it. So just knowing abstract properties of integrals. Looks to me like you're also going to need the fact that if you want to integrate from a to b, it is sometimes useful to integrate from a to c first, and then add the integral from c to b. So these are properties that are back in chapter 5 of the book. I remember the first couple of weeks, besides starting chapter 7, we were reviewing chapters 5 and 6. Looks like those are needed. Second problem, you're finding an area under a parabola. Just do the integral of it. Over the appropriate interval, you need to draw the graph of the parabola where it is across the x-axis. It's not too hard. You know, I can make that. I could make it a little harder. I can make it a little harder by making this equation more complicated. And if I give you this type of problem, I probably will. Make it a parabola still, but maybe something where you either have to factor it or use the quadratic formula. Here it's easy enough to see the x-intercept is going to be plus or minus 3. But I might make it more complicated. I might make it so you have to try to factor it first, or use the quadratic formula to find the roots. Would be a way I could modify a problem like that to make it a little tougher. But still definitely doable. So you should know the quadratic formula. If you're afraid you're going to forget it, you can put it on your piece of paper, again, that you can use for the exam, front and back. If you want to put the quadratic formula in there somewhere, if you're afraid you might forget it. Average value of function, just a matter of knowing the formula. and being able to use it. 1 over the length of the interval times the integral of the function gives you the average value of that function. I didn't ask for a geometric interpretation, though I'm not sure if one comes up on some other problem. But you should know geometrically that if your function, for example, looks like that the average value is the height of a rectangle that has the same area as the area under the original graph. That would be the geometric interpretation of average value. It's the height of a rectangle that has the same area as the area under the graph if the graph is above the axis. It gets more complicated if it's below or goes both above and below, but at least in that simple case, you should be able to give a geometric interpretation of the average value. And by the way, if the graph is concave up like that, the average value will be closer to the lowest point than it is to the highest point when the graph is concave up. Sort of most of, quote unquote, the values are in lower ranges than they are in higher ranges because of the concave. An intuitive way to think about that.
Wait, so I'm sorry. Did you say that the average value would be the height of a rectangle that's the area under the curve?
That has an area equal to the area under the curve, yeah.
Okay.
The height of a rectangle with the same area as the area under the curve.
Oh, okay.
And I tried to approximate it. Probably I made my rectangle looks like a little bit too high there. Looks like this area here is a little bigger than that area there, so I should have made my rectangle a little lower. Not too much lower. Somewhere in there. The height of such a rectangle is the average value of the function.
Thank you.
It's analogous to average speed. Right? If that were a graph of your speed, then the area under it is distance traveled. You go the same distance in the same amount of time if you stayed the same speed, your average speed the whole time, instead of accelerating and braking and stuff like that. So you can think of it physically too. Number 4 here typically gives people a little trouble. Calculate the derivative of this thing. Let me just talk about the general fact that you could use here. A more general fact you could use is that the derivative, well, first of all, there's the Fundamental Theorem of Calculus, which says if you differentiate an integral like this, you get the function that you were integrating. Emphasis on the fact that the variable for this function that you are differentiating is that upper limit of the integral. That is the variable for this function that is inside the parentheses. T is just called a dummy variable. You could use some other letter, U, W, whatever, tau. When you differentiate an integral where the variable is up there, the answer is the function you are integrating. Use an x though, because you want the same variable as the function you're differentiating. If you use some other function up there, some other function of x, like x to the 4th, let me just call it g of x, you have to realize that you also need the chain rule. The inside function is the original thing that was in the parentheses up here. Excuse me, that's the outside function. The inside function is g of x. The chain rule says take the derivative of the outside function, which is this integral. Its derivative is little f. Plug in the inside function here, which is the g of x. Inside functions get done first. If you were going to plug a number x into this expression that you see here, you figure out g of x first before you do the integral. So I need to plug the inside function into that, and then multiply times the derivative of the inside function. So for an arbitrary g of x, that's what the derivative of this integral would be. I didn't ask for it, but I could have also asked to, for example, find the first positive critical point of this function that's inside the parentheses here. Once you found the derivative, you'd set it equal to 0 and solve the first positive value of x. That makes it work. In this case, let's go ahead and write down the answer for the derivative. The derivative of this thing is going to be sine x to the 4th to the 3rd times 4x cubed. You see how that works? Look at this and look at what I wrote down at the bottom of the board. The g of x is x to the 4th. F of x is sine of x cubed. Look at this, compare with this. I'm plugging in g of x, x to the 4th, into f, which is sine of x cubed. So I got a cube x to the 4th, which gives you x to the 12th, multiplied times g prime of x. This is 4x cubed sine of x to the 12th. And so, for example, if you were looking for the first positive critical point of this function that's in the parentheses here with the integral, it would be where that function is first 0 when x is positive. If you set this equal to 0, that's going to be 0 for the first positive value of x when x to the 12th equals pi. So x would be the 12th root of pi. That would be the first positive critical point of this function with the integral there. That would help you graph that function with the integral, if you needed to graph it. Now again, I didn't ask for that, and I wouldn't necessarily ask for that on yours, but I'm wanting to add things like this. Just for your knowledge, I know just in case there's another problem that's similar to that. There's a pretty simple differential equation. In fact, it's a pure antiderivative problem. You're just after a function whose derivative is cosine, and also has an initial value of 3, just integrate. You're going to get sine of x plus c. Choose c equal to 3 to make it work. The answer is sine of x plus 3. Sine of x plus 3, with the plus 3 on the outside of the sine of x function. There's no y's on the right-hand side. This is just an x on the right-hand side. Just a pure antiderivative problem. Those are the easiest kinds of differential equations. Looks like a counting boxes problem here, or perhaps using a left and right-hand sum. Yeah, I guess it's left and right-hand sums. Oh no, I do say either count boxes. This graph is the rate at which water is flowing, the net flow from a water tower. When it's positive, the net flow is in. The water level is going up. When it's a negative rate, a negative net flow, water is going out faster than it's going in. There's the rate, the net rate. Inflow minus outflow is the graph we're seeing. It's got 5,000 liters of water to start with. What does the integral give you? What does the integral of this net flow rate give you? Does it give you the amount of water in there in the end? Or something else? Integrate a rate of change, you get the total change. Integrating this graph is not going to give you the amount of water. It gives you the change in the amount of water. You got to add 5,000, the starting amount, to the integral to get the quantity at the end of the month. So you estimate the integral. Looks like it's going to be slightly positive. It'll be this area minus that area. Add 5,000 to get your final answer. In general, an integral of a rate of change of a function gives you the change in the function. And if you know the initial value of the function, that can help you find the new value of the function. Looks like this is actually somewhat similar, except it's a formula instead of a graph. Spill of radioactive iodine. We're looking at radiation levels. The level of radiation decreases according to this formula. So it's decreasing according to the formula, and that's in millirems per hour. This is a rate of change. This is a derivative, even though you don't see an F prime there. You've got to see from the context that this represents a rate of change. And the units help too. That's why I added them. Or why the book added them. I think I took this from the book. 4.8 millirems per hour is the initial radiation level. It's a little confusing with the word level. By level there, they really mean a rate, not an amount. Millirems per hour. Total radiation is an amount in millirems, not millirems per hour. So, once again, the thing I just said 2 minutes ago still applies. The integral of the derivative, the integral of the rate of change, gives you the change in the function. In this case, the integral of the rate at which is the level at which radiation is being emitted in millirems per hour, is going to give you the total amount of radiation emitted. You need to do the integral to find the answer to part B. We integrate that function, which you can do by a substitution, right? If you want to do a substitution, this is simple enough that you could also just guess the antiderivative. But if you want to do a substitution, let W equal negative 0.005 t. dW would be negative 0.005 dt. You're going to end up dividing by negative 0.005 when you do the integral. In part A, that's not really a Calc 2 problem. Show work to confirm that's going to take about 415.9 hours to reach an acceptable level of radiation. They're saying at time 0, this is 8 times too high. It seems to me 8 times the maximum. The maximum acceptable limit must be 4.8 divided by 8, 0.6 millirems per hour. So it's just really a pre-calc problem, actually, for part A. Set this equal to 0.6 and solve for t using logarithms. But yeah, I think probably the hardest part about this problem is just getting your mind around it, right? What is it really asking you for? What does it all mean? That's, I've said that the past couple of minutes, but doing this problem cold, that probably is the hardest part. It's what does it all mean? How do you put it all together? What does it act? Realizing just do algebra in part A and do an integral in part B. The units are helpful in thinking that through. Maybe we should just quickly confirm the algebra. Solve 4.8 e to the negative 0.005 t equals 0.6. Solve that for t. Hopefully this is 415.9. Yeah. As you're reviewing, you've got time to test those kinds of things if you're unsure. And when you review, you should come at these things fresh. So I guess that was the mini exam, 2 pages. What was exam 1 like? Oh, that integral. That was not a super easy integral to do, right? It was a bit of a challenge. I think very few people got number 1 here on exam 1 and 3, right? Maybe we should just skip our break. Are we okay with that? So lecture A and B are now combining because we're about at break time for lecture A. Try to get us out a little early and to compensate. A couple minutes early. Told you what to do. Do a trig substitution to help you do this integral. let x equal 4 sine theta. And if you do that, you'll get square root of 16 minus 16 sine squared theta. If x is 4 sine theta, then dx is 4 cos theta d theta. So you're going to get out here a 4 cos theta d theta. This thing simplifies. You can factor out the 16. Square root of 16 is 4. You have a 1 minus sine squared theta, which is the same as cos squared theta by the most common trig identity to use. You're going to get a square root of cos squared theta, which is technically the absolute value of cos theta. Technically. But we always seem to be be able to get away with getting rid of absolute value signs in this class. And it does work here. Ultimately, the best justification is it works. It gets you the right answer. Maybe that's not the best justification, but it is a justification. Go ahead and get rid of those absolute value signs. Go ahead and write cos squared theta. Now there's another trig identity to use. A less common one. People forget it more often. So this is definitely one to put on your piece of paper. Cos squared theta is the same as 1/2 plus 1/2 cos 2 theta. Sine squared theta is the same as 1/2 minus 1/2 cos 2 theta. Both of these involve a cosine, which they'd have to, since these have to add together to give you 1. Sine squared plus cos squared has to equal 1. So if cos squared theta is this, sine squared theta has to be that, so that they add to 1. That helps you finish the integral. Your answer is going to involve then a sine of 2 theta and other stuff. You've got to multiply by the 16, you're going to get 8s in both spots. Your answer is going to involve a sine of 2 theta. I'm not going to write out the answer, but let me just think about the expression sine of 2 theta in this context. You want to replace the theta with arc sine of x over 4. And technically, if you do that and plug that in there, it's a correct answer, as long as you do the other parts correctly. However, it would be definitely good to simplify that. And it can be used simplified if you know another trigonometric identity. In this case, what's called a double angle identity. Sine of 2 theta is the same as 2 cos theta sine theta. And so then you can plug in the arc sine of x over 4 in 2 spots here and here. Sine of arc sine of x over 4 is simple, that's x over 4. For cosine of arc sine of x over 4, the simplest way to help you figure that out is to draw a right triangle. Remember doing this? The sine of this angle, by definition, is x over 4. Sine is, in this triangle, if this is the angle, opposite over hypotenuse. I can take this side to be x and this side to be 4. So then the sine of that angle is x over 4. And using the Pythagorean theorem, you can figure out the length of this side to be square root of 16 minus x squared. The cosine of this angle now is, oops, did I make a mistake?
Yeah.
I made a mistake. It's not a real big deal, but I mean, you get the right answer either way, but opposite over hypotenuse is sine. Cosine is adjacent over hypotenuse. Cosine of this angle is going to be square root of 16 minus x squared over 4. That's what this entire thing can be replaced by. To get you ultimately the answer in as simple a form as possible without any trig functions. This one was a matter of using numerical methods, doing ultimately the trapezoid method and the midpoint method. I did not ask you for Simpson's rule here. I'm going to say I could ask you on the final exam if I put this type of problem on there. Simpson's rule is not that much harder. Once you've got the trap and mid, remember that Simpson's rule for a certain number of subintervals n is a weighted average of mid and trap. It's 2 times the mid plus the trap divided by 3. It's a weighted average giving the midpoint rule two times the weight, because we saw with errors that the midpoint rule typically did twice as good. The error was typically twice as small than the trap was. The error. So I'm going to go ahead and tell you that even though there's not a Simpson's one on here, I might on the final exam ask you to do that, but it's not that much harder once you've got trap and mid. Just do this calculation. I think I did mention this, but then, by the way, there is another formula for Simpson's rule that involves the original partition points and function values. This is the approach our book takes. And I think it's a nice approach in terms when we thought about the errors and we noticed that the error in the midpoint rule was typically about half as much as the error in the trapezoid rule. This, I think, is kind of a nice approach to take because of that. It's sort of more of an experimental approach, you might say. This one's an improper integral that you also need to use integration by parts for. Making sure you carry the limit sign along, right? Improper integrals are really limits, proper integrals. So as you do the calculation, I'd want to see the limit sign. Do it by parts. You want to let u equal x and v prime equal e to the negative x. Find u prime and v. Use the formula of that. The integral of u times v prime is u times v minus the integral of v times u prime. Sometimes I didn't bother putting the dx's in there, but here are a couple more. Other books sometimes write this as dv here, and this is du. If you did it that way in the past, that's okay. This is the notation our book uses. But it's improper, carry the limit sign along. Conceivably, the integral might not converge, although it does. I did say take note of the fact that there's a 1 there rather than a 0. That makes the integral a little less pleasant to do. You should be able to handle it if I change the 1 to a 5. Four is a Mathematica question. I think I'll say it, I'm not going to put Mathematica questions like this on the exam. I'm not guaranteeing that for future classes, but for this class, I think that's not going to be an option because I do want to focus on the main content. Here's a question about errors in numerical methods. This might be something you've forgotten. So we're approximating an integral using n equal to 2 using these different methods. We get different approximations, different errors. Remember, first of all, the error, it goes in alphabetical order with the words actual and approximate. It's actual value minus approximate value. And I remember that by alphabetical order. Actual coming before approximate. So, for example, that means if your approximation is too big, then the difference here is negative. The error is negative. And if your approximation is too small, then the error is positive. It's a little counterintuitive. That's the way it goes. This approximation is, for example, too small. The error is positive. This one is too big. The error is negative. These are the errors for n equal to 2. What are the approximate errors? And they would only be approximate errors when n is 20 when you do 10 times the work. And going from 2 to 20 means 10 times the work, both for you and for the computer. The principle was that for the left and right hand rules, when you do 10 times the work, your accuracy goes down. Well, your accuracy goes up, meaning your error goes down by a factor of 10. You get one more digit of accuracy. So you need to essentially take these errors and just move the decimal point to the left by one spot. It's probably too many significant digits to write all these things, but go ahead and write them anyway. This is not an exact thing. In reality, what's probably going to happen is it would only be approximately this. And approximately this. But just for the sake of correcting the exam, go ahead and put all those digits anyway. With the trap and mid, each extra place of accuracy, each extra reduction in the error by a factor of 10, oops, I said that wrong. Each extra 2 places of accuracy, each reduction in the error by a factor of 100 requires 10 times the work. So we're doing 10 times the work. You're going to get 2 extra digits of accuracy. The error is going to go down by a factor of 100. So now in these, move the decimal to the left 2 spots. And so with Simpson's rule, if you do 10 times the work, you get 4 extra places of accuracy. The error goes down by a factor of 10,000, 10 to the 4th. Move the decimal to the left 4 spots with Simpson. Those facts that I just said in telling you what to do here are in your book, chapter 7. They are mentioned. In the discussion in section 7.5, for example, I see one fact that I mentioned on page 391. They say, in the trapezoid or midpoint rules, each extra 2 digits of accuracy requires about 10 times the work. That is an example of statement in section 7.5. It's italicized. It's not put in the box, but it's italicized in the reading. Does the function appear to be increasing or decreasing, concave up or concave down? If the function is increasing, whether it's concave down or concave up, the left-hand rule is going to give you underestimates. You can tell from the picture. And the right-hand rule would give you overestimates. It looks like the right-hand rule, though, is too low and the left-hand rule is too high in this example, so this must be a decreasing function, actually. And for concave up versus concave down, whether increasing or decreasing, but I'll draw these both increasing. Trapezoid rule always gives you an underestimate when it's concave down, and an overestimate when it's concave up. Trapezoid rule is too low when it's concave down and too high when it's concave up. It looks like this is too low. This must be concave down. It must be decreasing and concave down. Simpson's rule, in this case, gives you an answer too high. Actually, or excuse me, the midpoint rule. The midpoint rule can be thought of in terms of trapezoids as well, because the midpoint rule gives you an area of a rectangle like that, but what you can do with this rectangle is you can rotate the top so that it becomes a tangent line, and it has the same area still. So it's kind of a little funny. You can think about the midpoint rule in terms of trapezoids as well. And when the graph is concave down, the midpoint rule is going to be too big. That is mentioned in the book. They even draw a picture like that. Yeah, same page I was looking at before, page 391. Simpson's rule, you can't tell whether it's going to be too big or too small based on increasing, decreasing in concavity. Actually, Simpson's rule is more related to the fourth derivative of the function rather than the first, second, or third derivatives. But we don't get into that. Here is a parametric curve problem. Since we've been re-emphasizing parametric curve things recently, my initial thought in looking at this problem is I probably do want to put one like this on the test. As one example of one I'm probably going to put on the test. Probably for both versions. I do remember people had trouble with this one, especially with drawing the vectors. The equations were f of t equals t and g of t equals t to the 3 halves. You can use your calculator in parametric mode to help you graph it. And what you're going to get, if this were the example, let's see, 4 to the 3 halves is 8. When t is up to 4, you're going to end at the point 4, 8. This is going to be the ending point right there. When t is 4. It's going to look something like this. And I wasn't after the necessarily exact right picture. I think what I looked for when I graded it was the right starting point, the origin, the right ending point, the point 4, 8, because 4 to the 3 halves is 8, I'm looking right here. And the right concavity, it should look concave up. Ultimately, G increases faster than F does. Initially, F increases faster, but ultimately, G increases faster than F does because it's got a higher power once T gets past the 1. Actually, it's going to go through the point 1, 1 here, but I don't think I graded it based on that. I think I remember people getting this graph okay, but drawing the vectors gave people more trouble. The position vector, remember, always starts at the origin. And its arrowhead is at the location of the object. So there's the position vector. We'll label that position vector. What about the velocity vector? Draw the velocity vector. I said get the direction right and place the vector at the appropriate spot, but you don't get the length right. Actually, now you could get the length right. Or try to get it, at least it fits in the picture here. Its length is the speed, I've said that. At time 4 in this case. So that might be a change I could make to this problem, is I could say, get it the right length as well, or at least approximately, right? Speed at time 4 is going to be square root of 10 when you plug in t equals 4 there. It's a little bit bigger than 3. Make an arrow a little longer than 3 units. Approximately, you get full credit. It's got to be tangent to the curve. It points in the direction of motion. Actually, you could also, based on what we know now, get its components correct. I could ask you to actually write down a formula for the velocity vector. C of t here, f of t comma g of t is t comma t to the 3 halves. The velocity vector is the derivative of c. Write it in coordinate form if you like, or you can use I hat and j hat. The derivative of f is 1, so we get 1 times I hat. The derivative of g is 3 halves t to the 1 half. That goes times the j hat. At time 4, that would be I hat plus 4 to the 1 half is 2. 2 times 3 halves is 3. 3j hat. So, the velocity vector is going to have a horizontal component of 1 and a vertical component of 3. That means if you're at this point, you go to the right 1 and up 3. Yeah, you can get the velocity vector pretty accurate, which means my black curve picture is not perfect. But